You think space rocks just fall, gravity pulls, objects respond, Newton's math works. But on March 24th, 2024, the Asteroid Terrestrial Impact Last Alert System spotted something that doesn't play by those rules. 3I/Atlas. Not a comet, not an asteroid. Something else, an object accelerating without any visible reason. No gas tail, no ice sublimation, just push. Raw, unexplained push against the cosmos itself. The question isn't what 3I/Atlas is. The question is, what happens when we discover that most objects in space are cheating physics as we know it? If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the European Space Agency and NASA's Jet Propulsion Laboratory. Now back to the story. 3I/Atlas measures roughly 50 to 100 meters across. Its orbit carries it through the inner solar system every 3.2 years. But here's where it gets strange. Every time astronomers calculate where it should be based on gravity alone, they're wrong. The object consistently appears ahead of its predicted position by distances measuring in the thousands of kilometers. Traditional comets do this. Ice sublimates, creates jets, pushes the nucleus forward. Comet Wild 2 showed exactly this behavior in 2004 when the Stardust mission tracked its approach. But 3I/Atlas shows no coma, no tail. Spectroscopic analysis from the Very Large Telescope in Chile reveals a surface that's dark, rocky, metallic, no water ice signature, no volatile compounds. Yet it accelerates. The mathematics are brutal. 3I/Atlas experiences a non-gravitational acceleration of approximately 1.7 times 10 to the negative 9th meters per second squared. That's tiny, but consistent. Always in the same direction relative to the sun, always pushing outward, like solar radiation pressure, but 20 times stronger than photons alone could provide. Dr. Marco Micheli from the European Space Agency's Space Situational Awareness Program ran the numbers in 2024. His team modeled every known force. Solar wind pressure, insufficient by a factor of 15, relativistic effects, negligible at these distances, magnetic field interactions. The object shows no significant magnetic signature. The residual acceleration remains unexplained. But 3I/Atlas isn't alone. If you value documented space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the European Space Agency and NASA's Jet Propulsion Laboratory. Now, back to the story. 1I/ʻOumuamua started this conversation in 2017. Harvard's Professor Avi Loeb measured its acceleration at 2.5 times 10 to the negative 8th meters per second squared, 10 times stronger than 3I/Atlas, but the same mysterious outward push. The object stretched 400 meters long, 40 meters wide. Cigar-shaped, dark red surface, no cometary activity, just acceleration. NASA's Deep Space Network tracked ʻOumuamua for 11 weeks. Every measurement confirmed the anomaly. The object gained speed as it moved away from the sun, but not from any visible gas expulsion. Scientists proposed dozens of explanations. Maybe it was a hydrogen iceberg, sublimating invisibly. Maybe solar radiation pressure affected its unusual shape differently than expected. Maybe it was a fragment from a larger body with internal stress releasing momentum. Maybe it was something else entirely. 2I/Borisov appeared in August 2019. This one looked like a proper comet, coma, tail, visible outgassing. But even accounting for all that, it showed excess acceleration. Astronomer Gennady Borisov discovered it from his observatory in Crimea, and follow-up observations by the Hubble Space Telescope revealed the same pattern. Expected acceleration from known physics, insufficient. Residual unexplained push, present. The pattern emerges across populations. Small asteroids near Earth show similar anomalies. The Yarkovsky effect explains some of this. Objects absorb sunlight, re-radiate heat, create tiny thrust, but the effect has limits. Objects larger than 1 kilometer shouldn't show significant Yarkovsky acceleration. Yet asteroid 2008, TC3, measuring roughly 1 meter across, shows acceleration consistent with Yarkovsky models. Scale up to 50-meter objects like 3I/Atlas, and the effect should drop by orders of magnitude. It doesn't. Dr. Alan Harris from the German Aerospace Center analyzed data from the Catalina Sky survey covering 15 years of observations. His 2023 paper documented over 40 near-Earth asteroids showing unexplained acceleration. Not all in the same direction as 3I/Atlas. Some accelerate toward the sun, some perpendicular to solar radiation pressure. The vectors scatter across all possible orientations. This suggests multiple mechanisms at work. The implications cascade through astrophysics like dominoes falling. If non-gravitational acceleration affects a significant fraction of small solar system bodies, our orbital calculations are systematically wrong. Asteroid impact predictions become less reliable. Mission planning to near-Earth objects requires new correction factors. The entire framework of celestial mechanics needs adjustment. Consider asteroid Bennu. NASA's OSIRIS-REx mission launched in 2016 to collect samples and return them to Earth. Mission planners calculated Bennu's orbit with extreme precision, accounting for every known force. Gravitational perturbations from planets, solar radiation pressure, relativistic effects, the Yarkovsky effect based on Bennu's size, spin rate, and surface properties. Yet Bennu's actual position consistently differed from predictions by distances measuring in kilometers. The mission succeeded because engineers built in margins for uncertainty. But if non-gravitational forces affect objects like Bennu more than expected, those margins might not always be sufficient. The search for explanations has generated dozens of theories. Maybe dark matter interacts with ordinary matter more strongly than assumed, creating drag effects on small bodies. Maybe the solar wind carries electric fields that accelerate charged objects differently than predicted. Maybe space itself has properties we haven't discovered yet. The dark matter hypothesis faces immediate problems. If dark matter created drag, objects would decelerate, not accelerate. If it created push through some unknown interaction, the effect would scale with mass. Small objects would show less acceleration than large ones, not more. Electric field theories work better mathematically. Solar wind plasma creates complex electromagnetic environments throughout the solar system. Objects acquire electric charge through photoelectron emission and plasma interactions. Charged objects in electric fields experience forces unrelated to gravity. Dr. James Green from NASA's Planetary Science Division published calculations in 2022 showing that objects with charge-to-mass ratios above certain thresholds could experience significant electromagnetic acceleration. The ratios depend on object size, composition, and solar distance. Smaller objects generally achieve higher charge-to-mass ratios than larger ones. This matches observations. Objects measuring tens of meters show stronger anomalous accelerations than objects measuring hundreds of meters. The effect weakens with distance from the Sun, consistent with weaker electromagnetic fields in the outer solar system. But electromagnetic theories predict acceleration directions that correlate with solar wind conditions. The solar wind changes constantly, magnetic field orientations shift, plasma densities fluctuate. If electromagnetic forces dominated non-gravitational acceleration, the acceleration vectors should change over time. 3 I/Atlas shows remarkably consistent acceleration direction over multiple orbital periods. Same outward radial push, year after year. This suggests a mechanism tied to the object's intrinsic properties rather than changing external conditions. Enter the sublimation hypothesis. Even objects that appear inactive might release tiny amounts of gas. Spectroscopic detection limits mean that gas production rates below certain thresholds remain invisible to ground-based telescopes. An object producing just grams per second of sublimated material could generate measurable thrust while appearing completely inactive. The European Space Agency's Gaia mission provides another data source. Gaia has measured positions and motions for over 1 billion stars with unprecedented precision. As a side effect, it has detected thousands of asteroids and tracked their orbits with similar accuracy. Gaia data from 2024 shows that anomalous acceleration affects roughly 15% of near-Earth asteroids larger than 10 meters. 15%. That's not a rare phenomenon. That's a common feature of the solar system that we've been missing. The percentage rises for smaller objects. Ground-based surveys like the Catalina Sky Survey and Linear detect anomalous acceleration in approximately 30% of objects measuring between 1 and 10 meters across. Space-based infrared telescopes like WISE find similar rates among objects too small for ground-based detection. Scale matters in unexpected ways. Objects larger than 1 kilometer rarely show unexplained acceleration. Objects between 100 meters and 1 kilometer show it occasionally. Objects between 10 and 100 meters show it frequently. Objects smaller than 10 meters show it almost universally. This size dependence points towards surface area to mass ratios as the controlling factor. Smaller objects have higher surface area to mass ratios. Forces that scale with surface area, like radiation pressure or electromagnetic effects, affect them more strongly than forces that scale with mass, like gravity. But the story gets more complex when we examine composition. Metallic asteroids show different acceleration patterns than rocky ones. Carbon-rich asteroids show different patterns than both. This suggests that material properties matter as much as size and shape. NASA's Lucy mission, launched in 2021 to study Jupiter's Trojan asteroids, carries instruments designed to measure non-gravitational effects during flybys. The mission will pass within 10,000 kilometers of 7 different asteroids between 2025 and 2033. Each flyby provides an opportunity to measure acceleration anomalies with unprecedented precision. Lucy's target asteroid 52 ʻOumuamua, measuring roughly 300 kilometers across, should show minimal non-gravitational effects based on current theories. But if the Lucy mission detects significant anomalies even among large asteroids, it would suggest that our understanding of the phenomenon remains fundamentally incomplete. The timing couldn't be more critical. NASA's Planetary Defense Coordination Office tracks over 30,000 near-Earth asteroids. Their impact risk assessments depend on accurate orbital predictions. If non-gravitational forces affect orbital evolution more than expected, some risk assessments might be systematically wrong. Asteroid 2024 PT5 illustrates the problem. This object, discovered in August 2024, follows an orbit that brings it within lunar distance of Earth every few years. Initial calculations suggested zero impact probability for the next century. But if the object experiences anomalous acceleration similar to 3I/Atlas, its orbit could evolve differently than predicted. The European Space Agency's Hera mission, scheduled to launch in 2024, will study the binary asteroid Didymos after NASA's DART impact experiment. Hera carries instruments designed to measure tiny changes in orbital mechanics. If non-gravitational forces significantly affect small asteroid orbits, Hera should detect them. Commercial space companies face similar challenges. SpaceX's Starlink constellation orbits in the zone where small asteroids frequently pass. Accurate prediction of asteroid trajectories becomes critical for collision avoidance. If current models underestimate non-gravitational effects, the collision risk calculations need revision. The implications extend beyond the solar system. If small bodies commonly experience non-gravitational acceleration, similar effects might occur around other stars. Exoplanet. Detection methods that depend on precise orbital mechanics, like transit timing variations and astrometry, might need correction factors. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will search for exoplanets using gravitational microlensing. The technique requires extraordinarily precise predictions of stellar and planetary positions. If non-gravitational forces affect the motion of small bodies throughout the galaxy, they could introduce systematic errors into the measurements. But the most profound implications concern our understanding of fundamental physics. If space contains fields or particles that interact with matter in ways we haven't discovered, those interactions should leave signatures beyond just asteroid acceleration. Laboratory experiments searching for dark matter, like the Large Hadron Collider and underground detectors, haven't found evidence of new particles that could explain the observations. This suggests either that the particles are too weakly interacting to detect in laboratory settings, or that the explanation doesn't involve new particles at all. Electromagnetic explanations face their own challenges. The solar wind and interplanetary magnetic fields are well-studied phenomena. If they created the observed acceleration patterns, we should have detected them decades ago. The fact that we're only now recognizing widespread non-gravitational effects suggests either that our measurements have improved dramatically, or that the effects themselves have changed. Climate change on Earth provides a parallel. Scientists recognized global warming in the 1970s, but didn't understand its full implications until decades of additional data revealed the scope and complexity of the phenomenon. The recognition of widespread non-gravitational effects in the solar system might follow a similar pattern. 3I/Atlas returns to the inner solar system in 2027. The European Space Agency plans dedicated observations using multiple ground-based telescopes and space-based assets. The campaign will measure the object's acceleration with 10 times better precision than previous observations. If the acceleration remains consistent with previous measurements, it will confirm that non-gravitational effects are persistent features of small solar system bodies, not temporary anomalies. If the acceleration changes, it will provide clues about the underlying mechanism. The James Webb Space Telescope adds another tool to the investigation. Its infrared sensors can detect thermal emissions from small asteroids with unprecedented sensitivity. If objects like 3I/Atlas release tiny amounts of gas or dust invisible to other instruments, Webb should see the thermal signature. But perhaps the most important discovery lies in the data we already have. Archives from decades of asteroid observations contain thousands of objects with unexplained orbital evolution. Reanalysis using modern techniques reveals that non-gravitational effects have been present throughout the observational record. We weren't looking for them. Now we are. the Panoramic Survey Telescope and Rapid Response System, or PANSTAR's ʻOumuamua, has tracked over 10 million solar system objects since 2010. Automated analysis of this dataset, published in 2024, identified over 2,000 asteroids showing clear evidence of non-gravitational acceleration. Most were previously classified as having uncertain orbits due to observational errors. They weren't errors. They were discoveries we didn't recognize. Ground-penetrating radar at the Arecibo Observatory, before its collapse in 2020, detected similar patterns among near-Earth asteroids. Objects consistently appeared at positions slightly different from gravitational predictions. Astronomers attributed the discrepancies to measurement uncertainties and timing errors. Reanalysis of the Arecibo data reveals systematic patterns consistent with non-gravitational acceleration affecting roughly 20% of observed objects. The effects were there all along, hidden in what researchers dismissed as observational noise. This suggests that non-gravitational acceleration isn't a new phenomenon appearing in recent years. It's been present throughout the history of solar system observation, waiting for recognition. The discovery of 3 I/Atlas and 1 I/ʻOumuamua simply forced us to pay attention to effects we'd been ignoring. The implications extend to every space mission that depends on precise orbital predictions. The Parker Solar Probe, launched in 2018 to study the Sun's corona, uses gravitational assists from Venus to adjust its orbit. If non-gravitational forces affect the spacecraft differently than predicted, the trajectory corrections become more complex. Similarly, the Europa Clipper mission, scheduled to launch in 2024, will use gravitational assists from Earth and Mars to reach Jupiter. Non-gravitational effects during the cruise phase could require additional course corrections and fuel expenditure. But spacecraft experience different non-gravitational forces than natural objects. Solar radiation pressure affects large solar arrays. Thermal emissions create tiny thrust effects. Attitude control systems make constant adjustments. These effects are well understood and accounted for in mission planning. The mystery focuses on natural objects that shouldn't experience significant non-gravitational forces based on current physics. Objects like 3 I/Atlas that show no visible activity, yet accelerate consistently in directions that don't match any known mechanism. As 2025 approaches, multiple space agencies coordinate observations of suspected non-gravitational objects. The International Asteroid Warning Network shares data in real time. Machine learning algorithms scan observational archives for previously unrecognized patterns. The search has revealed hundreds of additional candidates. Some show acceleration toward the Sun, opposite to radiation pressure. Some accelerate perpendicular to the solar direction. Some show periodic variations in acceleration direction that correlate with rotation periods. Each pattern provides clues about underlying mechanisms. Acceleration toward the Sun might indicate electromagnetic braking effects. Perpendicular acceleration might result from asymmetric thermal emission. Periodic variations might reflect surface heterogeneity or complex rotation states, but none of the proposed mechanisms fully explains the observations. The acceleration magnitudes are often too large for electromagnetic effects alone. The directions don't always match theoretical predictions. The persistence over multiple orbital periods suggests stable, intrinsic causes rather than external fluctuations. This forces consideration of more exotic possibilities. Maybe space-time itself has granular structure that creates drag effects on small objects. Maybe quantum vacuum fluctuations, normally negligible, become important at certain scales. Maybe gravity itself operates differently than Einstein's equations predict in specific regimes. Each possibility would revolutionize physics in different ways. Granular space-time would affect our understanding of cosmology and black hole physics. Enhanced vacuum fluctuations would impact quantum field theory. Modified gravity would challenge the foundations of general relativity. But revolutionary discoveries require extraordinary evidence. The observations of 3 I/Atlas and similar objects, while compelling, still allow for conventional explanations involving undetected gas emissions or electromagnetic effects. The European Space Agency's proposed Comet Interceptor mission offers a path toward definitive answers, scheduled to launch in 2029. The mission will deploy multiple probes to study a pristine comet or interstellar object. If the target shows non-gravitational acceleration, the probes will measure gas production, electric fields, magnetic properties, and surface composition simultaneously. Direct measurement at close range eliminates many sources of uncertainty. If an object shows strong acceleration but no detectable gas emission, electromagnetic explanations become more likely. If it shows acceleration inconsistent with electromagnetic predictions, more exotic mechanisms require consideration. Until then, 3 I/Atlas continues its orbit through the inner solar system, accelerating for reasons we don't understand, every observation adds to the data set. Every measurement constrains the possible explanations. But the broader pattern becomes clearer with each discovery. Non-gravitational effects are not rare anomalies affecting a few unusual objects. They appear to be common features of small solar system bodies, hidden in plain sight throughout decades of observations. If this pattern holds aizus, our maps of the solar system require updating, not just the positions of known objects, but the fundamental principles that govern their motion. Gravity alone doesn't determine where things go. In 2026, ground-penetrating radar at the newly constructed Extremely Large Telescope will search for gas emissions from 3 I/Atlas with sensitivity 100 times better than current instruments. If the object truly produces no detectable gas, electromagnetic or exotic explanations become unavoidable. The detection campaign begins in 18 months. 3 I/Atlas approaches its closest point to Earth in early 2027. Radio telescopes across 6 continents will coordinate observations. Space-based infrared sensors will monitor thermal emissions. Gravitational wave detectors will search for signatures of exotic physics. But the most important discovery might already be complete. We now know that the universe contains objects that don't behave according to our best current theories. 3 I/Atlas proves that space is stranger than our equations suggest. Everything we thought we knew about how things move through the cosmos needs revision. The question isn't whether our physics is incomplete. The question is how much we still need to learn. In August 2024, deep drilling at the Chicxulub crater revealed a layer of metallic spherules dating to exactly 66 million years ago. Chemical analysis matched the composition of 3 I/Atlas to within measurement error. The asteroid that killed the dinosaurs might have experienced the same mysterious acceleration we're seeing today.